Hey, it's Mr. Shrum, and I am back again with a physical science tutorial. This should be the last one before our semester uh, break, and then we'll start second semester week after next because you get next week off. Next week is Martin Luther King Day, and yeah, that should be fun. You guys deserve a little break, right? But for now, we're still working. We're still trying to get as much done as possible. Last time we talked about the first law of thermo. Now we're going to look at the second law and how it relates to heat engines and entropy. So first, we're going to look at the intro. Scientists around the world are trying to find new sources and efficient uses of energy. So I'm sure you see on the news or on YouTube, hybrid cars, solar panels on homes, windmills, and those are just some examples of the ways scientists have harnessed energy and converted it into something useful for us at a low cost. That's the idea. We want to find a way to harness energy, make it useful for us, and hopefully that's not expensive to do. And one invention that has been attempted for centuries, hundreds of years, is the perpetual motion machine. And perpetual motion, that means the machine just keeps moving all on its own. No one has to intervene or make it do what we want it to do. It would provide endless output of ordered energy without any input of ordered energy, or at least it would put out more energy than it takes in. And sadly, nothing operates like that in reality. The first attempt was made by Robert Flood in 1618 when he created a water screw. And that's pictured here. Or well, this is an Archimedean screw. This machine recirculated water to its original container using a water wheel and a special device called the Archimedean screw. Many other inventors built upon Flood's idea in their own attempts to create the perfect perpetual motion machine. In this lesson, you'll study the second law of thermo, and in the most simple terms, this law states that entropy of a system never decreases, and entropy is the disorder of a system. That's how chaotic something is. And that means things do not usually become more organized in the real world. It's like if you drop an egg, once that egg is cracked, you can't uncrack that egg. That's sort of the idea, is that as time moves along, things tend to become more disordered and not more ordered. And we'll look at what that means later. But we'll begin this lesson with heat engines. Heat engines are devices that convert thermal energy, heat energy, think of that, into mechanical energy in the form of work. This concept ties into the second law of thermo, which states that it is impossible to transfer all of a device's thermal energy into mechanical work. You can't transfer all of the energy over into work. Nothing is 100% efficient like that. You're always going to lose some of that energy. And we'll also cover the entropy like we talked about. And that's how you measure the disorder in a system. Entropy allows us to calculate the change of one form of energy into another. Entropy is important to understand when studying how engines work and how the second law of thermo is actually carried out. Finally, we'll use entropy to calculate the efficiency of heat engines. And by the end of this lesson, you will master the second law of thermo. So let's get started. Heat engines. A heat engine converts thermal energy into other useful forms, like electrical or mechanical energy. The basic concept behind a heat engine is that when heat flows from a higher to a lower temperature, some of that heat can be converted into useful energy that can do work. All heat engines have three characteristic properties. First, the internal energy of the engine will be increased by absorbing heat from the area of high temperature. The second property is that some of that absorbed energy will be converted to work. Third property, the rest of that energy will be given off in the form of heat and will be transferred to a lower temperature reservoir. And we'll see how that works in the upcoming slides. There are various types of heat engines, but these are the general properties that are common to all of them. Would you recognize a heat engine if you saw one? Some common heat engines are gasoline engines in cars, steam engines that drive turbines in power stations, diesel engines that run tractors or trucks. So here's a car engine. If you guys drive yet or help your guardians out with their cars, you've seen this before. And that is a heat engine. And here's a diagram of what's going on. So we have the heat engine here. And then we have something called a hot reservoir at a high temperature. That flows into the heat engine towards the cold reservoir at a lower temperature. And as this moves to the lower temperature, you can convert some of that into work. So we'll look at each of these numbers. One, we have the hot reservoir. All heat engines need a source of heat. So this part of the model provides the heat into the heat engine. Then we have two. We have the heat engine. This device converts thermal energy into mechanical energy. It needs both hot and cold reservoirs. The heat is obtained from that hot reservoir. And then the cold reservoir is a sink where it collects heat. The heat engine itself converts the thermal heat into mechanical work. The cold reservoir acts as a sink. And a sink is something that attracts heat from a hotter reservoir. After the initial thermal energy passes through the heat engine, the energy that is left gets passed on to the cold reservoir. So what doesn't get converted to work gets passed on to the cold reservoir. Then we have four, work. The goal of a heat engine is to convert thermal energy into mechanical work. Some of the thermal energy taken from the hot reservoir can be converted into work. And then the rest is lost as heat and goes to the cold reservoir. QH right here, that's the input heat. That is the heat obtained from the hot reservoir. So think of hot TH, the temperature of the hot reservoir, and QH, the heat from the hot reservoir, is QH. Then we have QC, that is the output heat. The heat comes out of the heat engine and is transferred to the cold reservoir. So think of output heat to the cold reservoir as QC. All right, so which is an accurate statement about the work output of all heat engines? When the heat flows from a higher temperature reservoir to a lower temperature reservoir, some of that heat is converted into work. That is the correct answer. So we've seen how heat engines can create mechanical work as the thermal energy flows from high to low temperature sources or heat sources. But what exactly is work? Why do we say work? How do we measure it? Well, in terms of thermodynamics, work is the amount of energy transferred from one system to another. According to the second law of thermo, work is equal to the difference between the heat that goes into and the heat that comes out of the system. Work is equal to QH minus QC. W represents work. QH is the heat absorbed from the high temperature reservoir. QC is the heat that is passed on to the source of lower temperature. The difference between the two values is the work done by the system. Thermal efficiency is represented by E. It's defined as the ratio of the net work done by a heat engine to the heat absorbed during one cycle. If we substitute in the above equation, we get this formula. So what are you getting out of what you're putting in? So you're getting output over input. You're inputting QH. You're heating up that reservoir, and then you're getting out a certain amount of work. All right. And if you plug in what we just learned here, W is equal to QH minus QC, you can plug in QH minus QC, and then you wind up with this equation. E equals 1 minus QC over QH. When talking about efficiency, car companies always advertise fuel-efficient engines. What does that description mean? Engines that are more fuel efficient are able to convert more of the chemical potential energy in the gas into mechanical work. That means cars would use less gas to produce the same amount of work. So we've seen how heat engines ideally work and how we can calculate their efficiency. Now let's look at how they relate to the second law of thermo. The second law of thermo states that the structure of a system becomes more disordered. And another way to say that is the entropy or disorder never decreases. Since heat is a more disordered form than cold, it will never naturally flow from cold to hot objects. You can introduce an outside force to the system to reverse this movement, though. And that's how air conditioners and refrigerators work. In heat engines, heat always flows from the hot reservoir to the cold reservoir. Since some heat energy is always transferred to the cold reservoir by this natural process, that energy cannot be used to perform mechanical work. If some heat energy is lost, you can't use 100% of the heat input to do work. Bottom line, you cannot create an engine that does nothing other than take heat from one source and then perform an equivalent amount of work. Energy will always be given off along the way. Nothing is 100% efficient. That excludes the possibility of a perfect perpetual motion machine. Perpetual motion means it's 100% efficient. And that has not been the case. And that goes against, the laws of nature. A refrigerator can make heat flow from cold objects to hot objects. And that's the opposite of what would normally occur. But that takes energy to do. That's not natural. We have to input energy, and that's why refrigerators need electricity to operate and to do that work. The first person to closely examine the efficiency of heat engines was the French engineer Sadi Carnot. That sounds French, right? Before he did his research, most people thought that if you made a heat engine that had extremely low friction, it would be possible to convert all of the input heat into mechanical work. Carnot analyzed the processes of compression and expansion in various heat engines. And he made an important discovery. He realized that it was not necessarily friction that affected the efficiency of the heat engine, rather the temperature difference between the hot and cold reservoirs. So he came up with a hypothetical heat engine, and that's called the Carnot engine, that would convert the maximum possible amount of thermal energy into mechanical work. It's not possible to create a real Carnot engine. However, the Carnot engine accurately predicts the maximum possible efficiency of any heat engine operating between two given temperatures. Efficiencies of modern heat engines are compared to efficiency of the Carnot engine. So think of this Carnot engine as the ideal state. It's like the perfect engine that's as efficient as it can be. And in the real world, something tends to go wrong, but it's the measuring stick that we measure other engines with. And here we get the Carnot equation. So here we get a problem that we can work through together for a Carnot engine. And then after this, I think I will stop recording for today. But for a Carnot engine with a hot reservoir of 650 Kelvin and a cold reservoir of 310 Kelvin, what's the thermal efficiency? Well, we have the equation, the efficiency of a Carnot engine. And then you just identify what's TH, which is TC. Well, TH is from the hot reservoir, 650 Kelvin. Then we have 310. That's the cold reservoir temperature. And you just plug it in. 650 minus 310 divided by 650. That's 0.523. And in percentage, that's 52.3%. Here we have another question. We have a heat engine with a hot reservoir at 500 Kelvin and then cold reservoir at 200 Kelvin. What is the maximum possible thermal efficiency? So what's the Carnot efficiency? And we're looking for the efficiency denoted EC, so the Carnot efficiency. And then we need to use this equation, TH minus TC all over TH. Then you just plug in the answer. So which is the TH? Well, the hot reservoir says 500. I'll put K just in case. Then we have 200 for the cold reservoir, and then TH is still 500K. Let me check this. Okay, so don't put K's in there. Yeah, just have to put the numbers. Sorry about that. But that comes out to 60%. Okay. Not bad. All right, so that's it for today. And then we'll get into entropy next time. But until next time, have a great day and good luck with everything. Bye bye.